Good afternoon. Welcome everybody to the 2018 Hamvention Antenna Forum, formerly located in Dayton, now proud to be in Xenia. It's 2 o'clock on Friday afternoon, and we're going to have some fun. My name is Tim Duffy, K3LR. I have moderated this forum for 33 years at Hamvention. Thank you very much. I can tell you that some of the moments that we've had here, some of the eyeballs that opened wide, has been incredible over the years. And in fact, you can find slide decks for Antenna Forum presentations all the way back to 2004 on my website, which is www.k3lr.com. And very pleased today, and you can text your friends who are back home and not here, that this is being live streamed on Ustream. So you go to Ustream and you look for DARA, D-A-R-A, live. And the Antenna Forum is being streamed live on the internet. So that's very, very nice. And thank you to Dan W8AAU, who is Vice President of DARA. Thank you very much for your help here today, Dan, as well. And if you have ideas for next year for the Antenna Forum, make sure you send me an email. It's k3lr@k3lr.com. And today we have 4 very, very, very good papers. I hope you stay to watch all of them. I can tell you throughout the afternoon that this place will become entirely packed. Every seat will be filled. So please make room for others as they arrive. Each talk will last approximately 40 to 45 minutes long, so you can give some ideas to the planning of your time. Our first talk is a 5-element parasitic rotatable Yagi for 160 meters. Our speaker is very well qualified to do this. He's been a DXer and a top band advocate for many, many years. He is also a former ARL president. Please welcome Joel Harrison, W5ZN.
Take that to heart. Thank you very much, Tim. As Tim said, I'm Joel Harrison, W5ZN. It's quite an honor for me to be here again. This is the second time I've had the honor of presenting at the Dayton Antenna Forum. I live in Arkansas, about 50 miles northeast of Little Rock, where my station is located. And I have no other hobbies. I have no time for other hobbies. I barely have time for a job. And as such, my wife refers to me as a professional amateur. So I really get into a lot of projects here. So what I want to talk about today was a project that I became very passionate about last fall, and that is an antenna system that would give me some gain and some directivity in different directions, switchable on 160 meters. So the reason I needed a new transmit array was that for about the last 10 years I've been perfecting my receive arrays for 160 meters. I started out about 10 years ago working with a broadside end-fire 8-element vertical array for receive for 160 meters. Bob McGuire in 4HY and I had published a paper on that, and then we revised that into a second edition this past last year, and invited Frank, W3LPL, to be one of the co-authors as well, as Frank put up one of the arrays and has quite a bit of experience with it. I also then later on installed a high Z 8-element array for 160 meters, and last year I also put up one of the YCCC 9-element arrays as well at my place, and a couple of other beverages. So, you know, I have enough land that I can experiment with receive antennas, and I've reached a comfortable level now But I started to really feel like I was deficient on my transmitting side, because I only had a single shunt-fed tower that I was using for a transmit array. I had confirmed 260 DXCC countries on 160 meters, but I was becoming stagnant. You know, the countries that I needed really were much more difficult to work. So just trying to work them without a gain antenna was becoming very difficult. So I needed some extra gain and directivity to advance my DX standings, and to also try to really be competitive in some of the contests, the DX contests on 160 meters. I have a very good 80-meter installation that I use, and I'm very competitive there from Arkansas, but it's difficult on 160 meters. So I spent well over 2 years really in a state of trying to figure out what to put up. As I said, I had plenty of land. I could put up a 4-square array, but that was an effort that I just really didn't feel like I wanted to get involved in, because I would have to put up 4 complete new quarter wave structures, and it was going to be just really more than I felt like I wanted to do. So one night I'm kind of thumbing through low band DXing again, just revisiting some of the arrays in there, and I came across the section on the arrays with parasitic elements. And I studied this for about 2 weeks, and literally started becoming obsessed with that design. And in that design, I noticed that Tim K3LR had a version that he had put up at his place and was using. So obviously, once I looked over that, the next step was I couldn't stand it. I had to get on a plane, fly to Pittsburgh, and knock on the door and say, "Hey, Tim, here I am. I want to look at some of the antennas here." So I did that, and after looking at that, and then later on in the fall last year in September, down at the 6-meter barbecue in Austin, and you may be wondering, why in the world were you talking 160 meters at a 6-meter barbecue? If you become obsessed with an antenna project, you'll go to a ham buddy's granddaughter's dance recital if you think it'll give you an opportunity to talk to him about it. So that was one of the reasons I was down there. So after that, I became convinced that this was the perfect array that I needed to install at W5ZN. So what were my reasonings for doing that? Well, number one, the array could be built around the existing transmit vertical that I had. I didn't have to move over somewhere and put up 4 separate big quarter wave towers or some kind of big elements for a 4-square. I could use that existing transmit vertical that I had in place. I really didn't need full-size elements. I could use shortened top-loaded elements for the parasitic parts of the system. The existing land area around the transmit antenna could be utilized. So I didn't have to go out and try to make sure I had a completely different area all cleared off for a 4-square. I could use that landmass right under the tower. A 3-element or a parasitic array would give me the same basic gain in front to back ratio that you would realize in a 4-square with a 4-square array, and it would still be switchable in 4 directions. The feed system for this was extremely simple. I didn't have to change anything on the feed system. The existing feed system on my quarter wave vertical that I was using could still be used. I didn't have to use any new phasing or complicated schemes to change that. So that was a plus. And it gave me a slightly smaller footprint for total area than a 4-square would have. So if you take a look at the gain of a parasitic array, and this is a parasitic array with 3 elements, you know, you still have basically 25 dB front to back ratio. You have a very good broad pattern here on transmit that you can use. So it was very comparable to a 4-square array. Now, a vertical Yagi array with parasitic elements was really popularized several years ago by Bill Hohenstein, K0HA. And I mean, Bill he just wouldn't use anything else on the low bands. He believed in these arrays, and he was very, very effective with them. And he was loud in a lot of places. And A parasitic array is comprised of 3 or more vertical elements with 1 active element, and the rest being parasitic. Now, I know some folks have experimented with just using 1 parasitic element, maybe as a reflector, 1 as a director, and that does give you some benefit over a single vertical. However, you do not get the real refinement of the pattern and the directivity that you really want to have if you do that. So that's why most of these are 3 elements. Currently in use at AA1K, VE3EJ, K3LR, NR5M, and K9CT is this array. So if you haven't been asleep over the last few years and you've heard these stations on the air, you know they're very, very effective on 160 meters. John actually went in and added a second director toward Europe to his 3-element array, and it actually added about another 0.9 of a dB forward gain for him. So there is some expandable options if you wanted to do that. The parasitic array is really comprised of top-loaded vertical elements. You know, top-loaded vertical elements, parasitic elements, they're extremely effective. And the real nice thing about them is they can be suspended from catenary ropes from an existing vertical array. You can hang a rope off from, for example, my tower that I had already, shunt fed, and put a rope on here, tie the top-loading elements, and then drop your vertical portion down from there. So it was very, very simple to add these additional elements. Top-loaded vertical elements can be resonant with a shorter length than a quarter-wave full-size element. Now, when you start adding a horizontal element to a top of a vertical element, you need to really start wondering about what you're going to add as far as any horizontal component to your RF wave. But if you go in with a top-loaded element and it's symmetrical with the vertical element, in other words, if the vertical part is tied directly in the middle of your top-loaded element, then you're not going to have that horizontal component out in the far field. All right, you're going to maintain a vertical polarization. So that's a very important thing to understand over maybe an inverted L-type element or something of that nature. The top-loaded segment is going to be somewhere in the vicinity of 60 feet. That's going to vary a little bit, and we'll talk about that more here in a few minutes. The vertical part's going to be around 70 feet or so. So you can see that with just 70 feet of height, you can achieve an effective element on 160 meters. So when I started trying to, after I had really decided, okay, this is what I'm going to do for an array, and I started laying out this project in my head, I really organized it into 5 different phases. One was to do the physical layout. Next was to understand and lay out the radial system. Then go into the element construction and erection, tuning it, and then switching the parasitic array. The physical layout is very, very simple. You can actually complete that in probably 30 minutes or less. I mean, you have your existing tower that you're using, okay? So you just need to put out 4 areas where you're going to drop the parasitic elements to. They're spaced 66 feet from your driven element tower. All right, so in other words, for this direction here, looking northwest, all right, those 2 elements are spaced 66 feet from the tower. So a total of 132 feet, all right? Excuse me. And then you want to lay these out 90 degrees, simply just as you would a 4 square, around the driven element. The radial system now is going to be the most complicated and time-consuming part of this project. But you need to understand, it is by far the most important part of it. All right? Parasitic arrays have a greater impact from a poor ground system than driven arrays. Elevated radials aren't going to work. So if you're sitting there thinking, yeah, I could put up one of these arrays and I could throw out some elevated radials, not going to work, all right? It just doesn't work with a parasitic element. John, ON4UN, modeled a number of different elevated array configurations, and he talks about this in low-band DXing. And he just never could achieve any kind of a decent pattern when he did that. With a phased array, like a four-square, okay, and if you stop and think about this just a moment, you're actually driving, you're feeding or driving each element in a four-square array. So you're forcing the currents into each element, all right? With a parasitic array, that doesn't happen, all right? It's a parasitic array, it's hanging out there, and it's kind of like a sponge, you know, it's soaking up your RF energy. But if you don't have a good ground system, the current distribution is going to really, really suffer. And if you don't have good current distribution, it's going to impact the gain. So it's really effective that you have a good ground system. Here's a little chart that kind of shows the gain of a three-element array as a function of ground loss. You know, if you look up at case A here, you know, that shows on the plot that if you have a driven element that has basically 1 ohm of ground resistance, but you don't have very good ground resistance under each of your parasitic elements, you know, your gain can suffer by up to 3 dB. So that really eliminates your purpose of trying to put up a gain array like this. All right, so how many radials did I use? 120 radials under each element. Now listen to that. That's not 120 radials total. That is 120 radials under 5 elements, a driven element and 4 parasitic elements. So you have a total of 600 radials. And the radials are all tied together, all right? If you're familiar with laying out a four-square system or anything of that nature, you always lay bus wires, right, inside the square to where those radials that will intersect are tied together. Same process here. But in addition, to start out from the driven element, all right, I have a bus wire laid out that is about 0.09 wavelength, 48-foot diameter, and we'll look at that here in a second. 48-foot diameter. So everything from the driven element, the tower, there's 120 radials that go out to this 48-foot diameter bus wire. And then from there, all of the radials from each of the parasitic elements runs out, and they're either tied at the perimeter wire around the driven element, or they're tied to the bus wire that runs in a fashion across there. So, how much radial wire do you think I have in this system? How much? 10 miles? You're somewhat warm. Only one guess? All right. I ended up with 13.7 miles of wire in the radial system. 22,000 kilometers. All right? It takes that. That's not meant to scare you off if you want this type of an array to be effective. And it's a lot easier laying radial wires on the ground than trying to put up 4 big quarter wave elements and then have to put up a ground system the same underneath it as well for like a four-square. So here was my radial construction procedure. The first thing that I did was to go in and put the 120 radials out from the tower, the driven element, out to this 48-foot diameter bus wire that goes around it, all right? And I started on the radial system first. And the reason I didn't go in and start constructing any of the rest of the array was because I said, you know what, this is going to be the most challenging part. If I get halfway through it and I say to heck with it, I'm not doing any more, I haven't really wasted anything because what I've done has added radials underneath my single transmit vertical. All right, so I would be left with some slight benefit. So I started with the radial system, going around with 120 radials. That went relatively easy and relatively quick, and I thought, this is going to be a piece of cake. Then I started installing the radials that would go from each element that would intersect with this perimeter wire, all right, and I installed all of those. Then I moved on to install all of the radial wires that would intersect this cross bus wire here, okay? And I got those installed. Then the last thing that I did, which was the very easy part, after doing all of that, was just install the remaining full quarter wavelength radials from out of each element. So I don't know how well this shows up back there to you, but you can see the bus wire here, which was a number 4 solid copper wire running in a 48-foot diameter circle around my transmit tower here. And all of the radials from here go out and they attach to that. Here's another shot of it laying on the ground. Now what I would do, I would go out with my radial wires and wrap them and solder them to this bus wire, okay? Then I don't know if you can see this very well, but then as the other wires come in from the other elements to this bus wire, here, there's one coming from the tower and a couple over here. They're all the same wrapped and soldered to the bus wire. And then I take liquid tape or some other really good insulating material and coat those to protect that solder connection.
Silver solder?
I don't use silver solder, Don. It's just regular good quality solder. Here you can see some of the radials that are going from one of the elements over to that 48-foot bus wire. So there's several of them there on the ground. You can use any really sound method you want to for connecting the radial wires to the elements. I really like these radial plates that DX Engineering sells. These are stainless steel plates. They have pre-drilled holes in them. You can use bolts to secure the radials to the plate. And those things are just darn good. I mean, it's stainless steel. It's thick, high quality. It doesn't ever rust. It doesn't get bothered by the elements. And it gives you a really excellent connection for your radial system. So that's what I use. I also then take the radial wires that connect to this and I crimp them to these ring terminals, and then I solder that also and then connect it to the radial plate. Now I also like to put down a little bit of penetrox. There's kind of a lot laying there on one of those holes, but put a little penetrox on that because the ring terminals are probably, there's some tinned copper or something of that nature. Your radial plate is stainless steel. Those are dissimilar metals, and a lot of time, you'll get some galvanic corrosion over time, if you're not careful with that with dissimilar metals. So, it's an easy step that you can do that will help ensure a good electrical connection. So here is one of the completed radial systems under one of the elements, all right? You have 120 radials coming out from it, all connected to the radial plate. Now, I like to use, you'll notice those little white things at the bottom. Those are some of those biodegradable radial staples. I like to use those just to pin down the radials on the grass and to keep them in place. And I'm going to talk a little bit more about how I do radials, but I like to put those down. They're really good and they're easy to use. I had a ham buddy of mine, when I mentioned that, look at me real funny and say, let me get this right. You put 13 miles of wire down on the ground and then you wanted to use a biodegradable staple? I told him, yeah, I'm concerned about the environment. Total area of the radial system of all 5 elements took up just a little under 2 acres. All right, so by the time you got everything all fanned out, a little less than 2 acres. And it took me 4 weeks to complete this. Now, I mentioned a little bit earlier I became obsessed with this array. So much so, I just finally had to tell all the folks that work for me in my office, I said, you guys take care of things. I've got a problem I got to take care of at home. Then I walked in and told my wife, I'm going to work on a project here, antenna project, so I'll be out here for a few days. After 2 weeks, and I was probably going out there about 6 hours a day, my wife finally looked at me one afternoon after 2 weeks and said, how much longer do you have on this project? And I just said, until I'm finished. So at the end of about the fourth week, when I finally staggered in the back door and stood there and pronounced that I was finished, she just looked at me and said, "Thank God. I hope you don't have another one of those projects in the bag." I do. So let's talk about the element construction here. All right, these T elements. Each element now is going to need to function as a director and as a reflector. All right? So they're going to have to be electrically a little different. So to accomplish this, all right, if it's a director, it's simply connected directly to the radial system and tuned to a certain frequency we'll talk about here in a second. If it's functioning as a reflector, it needs to be a little bit lower in frequency. So we simply switch in like a 4 microhenry inductor or something to lower the frequency, and then it's connected to the radial system, and it works fine. The vertical top load links are sort of a trial and error. You build one element and get it all tuned up and everything, and then the others are going to be that length. I mean, they just fall right into place. If you're going to do this, when you start hanging the elements, make sure you hang the first one up there with a rope and a pulley. Otherwise, when you start tuning it and tweaking it a little bit, you're going to really get in physical shape by climbing that tower about 23 times. It's easier just to lower a rope. The distance from my tower of the driven element out to the start of the top loading mine is around 45 feet, something like that. And then the distance out to the far tie point from the tower is about 265 feet. And I just drove a T-post into the ground and tied the rope to that. So when I started looking at the lengths for the top loading, ON4UN had modeled some lengths in low band DXing, and he was targeting the resonant frequency for his directors to be around 1935 kilohertz, and the reflector about 1778. And he had lengths of about 65 feet for his top loading element, part of the element, and about 75 feet for the vertical element. Now, Tim's system is described, and Tim, in his research, had concluded that the real target frequencies to achieve maximum front-to-back ratio and forward gain was 1800 kilohertz and 1904 kilohertz. So what I thought I would do is go in and just use Tim's dimensions for the elements first. That didn't work at my location with my installation, all right? Because when I did it, you can see that my resonant frequencies were a little way too low. So what I actually wound up with for my installation were almost the exact lengths that ON4UN had modeled. So, you know, your mileage may vary a little bit, but this gives you the lengths that you can start with. Start with the longer elements, all right? I started with the short elements, so I had to build some new ones. So, to tune these elements, you know, you basically connect an antenna analyzer, you know, between the vertical element and the radial system, just as I've shown here. Then you want to switch in the vertical wire directly to the radials and trim it for the frequency you want it resonant for. Very simple to do. It's an easy part. Then, once you finish that, just switch in the vertical wire through the inductor to the radials, and you can spread the turns on the inductor to change the frequency a little bit and get to where you want to be. Now, this system, the way it's designed for switching, has an omnidirectional mode, where all four of the parasitic elements are floating. However, there's a difference in the feed point impedance characteristics when it's omni than when the array is active. And I will confess to you, I spent an entire day trying to figure out why, when I tuned for my resonance on the omnidirection, just the array, and then when I switched in the other directions, I never could get them to agree. I knew, this is kind of funny even if I knew I'm interacting with something. And I was pulling my hair out trying to figure out what in the world is this interacting with. Well, finally one night it's like, wow, I could have had a V8. Yeah, it's interacting with the parasitic elements, you dummy. That's what it's supposed to do. So there's going to be a little bit of difference. So, you change it really, you tune it for, with the active elements, all right? Not with the omni. The main purpose really of the omnidirection is it allows you to be able to compare gain in different directions, to switch it in and back. So make final SWR adjustments with an active array. You should realize a 1-to-1 SWR and the 1.5 to 1 bandwidth is going to be about 40 kilohertz. Here's a plot that I made initially once I realized that, what I needed to do to get it tuned right. And I went in and did some tweaking on this later and actually got the resonant point down to 1-to-1. Really, really nice. But you can see there's a real good 40 kilohertz bandwidth here of the array. Works real nice. So if you want to do some real fine tweaking here with the array, there's kind of a unique procedure that you can do, and that's to go out about a mile or two out into the opposite direction. In other words, if you select northeast for your direction of the array, go out to the southwest a mile or two and have someone transmit a low-level signal, and then just adjust the spacing on your inductor to achieve the maximum front-to-back ratio, all right? And that will tweak up the forward gain as well. Very simple to do. So what about array switching? Well, I had the luxury of Greg Orty, who had designed a circuit board for Tim to do some switching, and I was able to get some of those to use. And these are the boards, one at each of the parasitic elements. It contains 2 relays, one that will be active when it's a director, the other that will be engaged when it's a reflector. Here's the inductor, all right, when it's switched in to operate as a reflector. And then, some other components to help with filtering and bypassing and that sort of thing. And one of these is at each element. Switching in the shack was very simple. I actually brought out of some of my unused stuff an old Ameritron 5-position antenna switch box that I used, and I pressed that into service to switch in each direction that I wanted. So it's very, very easy to do, not complicated. So here is one of the relay boards inside a plastic box out at each element. Put it in a plastic box because I wanted to make sure that the element, as it came down, was insulated from any grounding and so forth. So the easiest thing to do was just go pick up some of these plastic boxes at Lowe's, Home Depot, or wherever. And as I said, the element comes down and is attached here on the side of the box, feeds into the switching, and then goes down to the radial system below it. So you may be sitting there right now asking, what the heck is that big roll of cable doing around that box? I thought this was a parasitic array, you didn't have to feed it. Anybody have any idea what that is? That's a quarter wave shorted stub on 160 meters, and there's a reason for that. The reason is this array, or a couple of the elements, is very close to my 80-meter foursquare. So if you stop and think about it, a quarter wave shorted stub on 160 meters is really invisible at the feed point. It's open, right? However, on 80 meters, that's a 1/2 wavelength shorted stub, so it looks like a short to 80 meters. So it eliminates, minimizes any interaction between these two arrays. If you can, I don't know how washed out this is, but here is my foursquare sitting back over here for 80 meters. Here is the transmit antenna, the driven element. Here is the northeast parasitic element, the southeast parasitic element, southwest, and then northwest. So the southeast element actually sits only about 60 feet from my foursquare. So by doing this, it knocks out any interaction between the two and works really, really great. One other thing I'm going to point out here, you see the guy wires running down here from this tower, and they're only about 2 feet from the northwest element. And understand that you're going to have to make sure your guys are insulated so you don't wind up with any interaction. That's actually Philistrand guys, so I don't worry about anything on the tower at all. So, the array's all installed, working very, very good. What are my results? I realize about 5 dB of forward gain and 25 dB front to back. It's performing like it was modeled, and it meets my expectations. RB and reverse beacon network reports indicate it is a significant improvement over my single vertical. I've noticed a significant improvement in pile-ups. So if you don't believe what I say about the array, maybe, just maybe, you'll believe what Jeff Briggs has to say about the signal. He was the 160-meter operator at Spratley here recently, 9M0W. And Jeff said, your signal was better than most about RST 339, which may not sound loud, but compared to all the others who were 219, you were loud. That was worth my effort. All right? I want to give some acknowledgments here right quick. I really could not have completed this without the help and advice from Tim. Tim, thank you so much. I really appreciate that. John Thames, AA1K, once I found out he had an array, he just was a wealth of information as well. And then Larry Burke, K5RK. Larry didn't help me one bit with the array and building it. Larry lives down in South Texas, all right? And he's always infuriated me. He's a real good friend of mine, but he can work stuff and I can't. That ended November the 1st, all right? That's all I have. Thank you all very much. I'm around. If you have any questions, just see me in the back, or I'll be at the contest suite here a little bit later. Thank you all very much.
Thank you, Joel. It's a tremendous presentation, and I'm really glad that you put in 4 weeks of work on your hands and knees, and it paid off. It's nice to see a project go from modeling state all the way to working a new one. So let's go to our next presentation. So a couple of things. What's new this year is there's a survey form in the back table, and it's a Dayton Hamvention Forum evaluation form. So if you would, at the end of all the talks today, fill one out and let the Hamvention folks know what you think about what you saw here today, if you liked what we did, or you didn't like what we did. We are live streaming on Ustream under the DARA Live channel, and previous year's slide decks for the Hamvention Forum, the antenna forum, are available at the k3lr.com website since 2004. Our next talk is a pragmatic approach to 630 meter antennas, and our speaker is very well qualified on this subject. He's done a lot of work. He had an experimental license on the band for several months, maybe even years, I guess, as he did a lot of research. And I'm very excited to have this new band getting new antennas and new ideas out here. Please welcome Eric Tugansky and O3M.
All right, thanks, Tim. Good afternoon, everybody. We're going to talk a little bit about 630 meter transmit and receive antennas, hopefully get a better understanding of how to build effective antennas for the band, and hopefully debunk some myths that are out there about effective 630 meter antennas. Is that it? On the screen, okay, there we go. Nope. There we go, all right. Just a quick intro to 630. It covers, as far as hands are concerned, 472 to 479 kilohertz. It's in the medium frequency region, which includes AM broadcast and the 160 meter band, and is characterized by daytime delay or absorption, though in some cases during the middle of winter we actually do have skip propagation during the middle of the day. And of course nighttime E-layer reflection. Wavelengths, one wavelength on 630 is about 1,000 feet. And as far as amateur operation on the band, there really hasn't been any since the Spark days prior to 1912, which of course was stopped by the Radio Act in 1912 that limited amateurs to 200 meters. In the late 90s and up through the early 2000s, some entrepreneuring amateurs applied for Part 5 experimental licenses, including the ARRL in 2006, and were granted the call sign WD2XSH. And that was a large block grant which included a lot of stations around the country, including Alaska and many states. And they operated up until the point where the band was assigned for amateur use by the FCC. So they laid a lot of groundwork in getting us the band. It was formally allocated during WRC 12 as a secondary allocation for amateur use. And of course, the FCC, it became official on September 15th of last year. And written in the Part 97 rules. However, the first transmissions didn't occur until about October 14th because there is a notification process that must take place. You basically submit a notification to the Utilities Technology Council, and you have to wait for a 30-day waiting period, and if you don't receive a denial within that time period, you can proceed to transmit. So there's been some talk of people waiting for an approval, and that's not necessarily required or stipulated in the rules. So as long as you don't receive a denial in that 30-day period, you're good to go. And as far as activity goes, do we have any active 630 operators in the audience? No, they're all hiding in the back. But at this time, we have 111 active stations that actually have recorded QSOs, and that's covering 39 states, including Alaska and Hawaii. And some of the top operators have worked anywhere from 28 up to 36 states to date. So it's definitely possible. Once more states get active, we should be seeing stations getting worked all states within a short period of time. And interestingly, many operators coming down to 630 are from a VHF and UHF background. So apparently there's something attractive on both ends of the spectrum. As far as propagation, it's very similar to 160. We see gray line, sunrise and sunset enhancements, solar events, specific things like solar flare enhancements. Vertically polarization is generally the best way to couple to the ionosphere, and that applies to medium and high latitudes. When you start getting near the equator, things change a little bit. We do see prominent north and south and east and west paths at times. And as far as QSB, I was actually just having a discussion with another 630 op. Back in the old days, they used the term fading. And essentially, we see a very slow acting fade cycle, or QSB. And a lot of times it's superimposed on an even longer QSB cycle. And on any given night, you could actually set a clock to it. It could range anywhere from about 6 to 10 minutes. It's very consistent, and operators that are aware of this Let's say you're trying to make a JT9 QSO and things start to fall apart. If you just wait for the so-called known period of time for the fade to come back up, chances are you'll finish the contact. And there's been many documented cases of that, both under the experimental licenses and under amateur operation. And as I said before, we can have long-range daytime propagation. A contact between myself and, at the time, WG2 XIQ in Texas happened on January 30th, 2015 at basically solar midday, which is an 1,116-mile path, so well beyond ground wave. As far as QRN, you're looking at anywhere from 6 to 24 dB higher than 160, or about 1 to 4 S units. Now, as far as myths go, and I've heard these many, many times, actually not longer than probably 15 minutes ago, you need a high-efficiency transmit antenna is one that often comes up, or you need loads of power or acres of property. And as we go through the rest of the presentation, we'll debunk those with some effective examples. Another one is 5 watts EIRP is not enough to work any DX. And at the moment, we have many DX contacts documented, including V7SL in British Columbia, who made contact with VK4YB. And there was actually at one point an opportunity for myself to make contact with VK4YB, but unfortunately during that opening, I was still in bed. So. Other examples are AA1A, N1BUG, which many of you may recognize from 160. Myself and K9KFR have had QSOs with Europe. Those are using JT9. And we have ZF1EJ that's very active on the band, has had QSOs with amateurs all around the country, including V7SL. A couple cards there of Steve's actually showing ZF1EJ and VKYB confirming. And another myth is that it's only a digital band. Now, many of the long-haul contacts at the moment are JT9, but CW will be possible when we get better conditions. I've had 112 CW QSOs within the first 5 months. Many of them included rag chews, as well as contacting KH6. And there have been a few single sideband QSOs. And there's really not much of a limit on the type of modes you can use. So sideband, even if you want to go as far as AM, but I would recommend not using AM because the bandwidth will pretty much take up the entire 7 kilohertz. As far as the FCC rules, really understanding how to build an effective set of antennas is in the rules. We have a maximum antenna height of 60 meters above ground. Now that may not sound very tall, that's approximately 195 feet, but we can achieve very effective antennas well below that height. And let's see here, transmitter power can't exceed 500 watts. Again, that doesn't sound like much, but as we go through some examples, we'll see that that kind of power generally is not needed, and if we do require that much, we're going to have some other problems, specifically high base voltage that we have to deal with. The radiated power can't exceed 5 watts EIRP, and this can be a somewhat foreign concept because most of our power limits have been based on transmitter output, or recently on 60 meters ERP, which is very similar. So what exactly is EIRP? It's basically the power radiated by an isotropic antenna that results in the same radiation intensity or power density at a given distance as an actual antenna in the direction of its highest gain. So we've kind of given a graphic example here to understand it a little better. The first example shows basically the sphere represents the isotropic radiator, and that the outer pattern is the standard pattern for a vertical monopole, and they both have the same radiated power. But we can see that the vertical has a higher power density because of its gain over an isotropic radiator. So to basically enclose the power density, or make the power density at any given point on the verticals pattern equal to the isotropic radiator, we have to reduce the power to the vertical. So as a specific example, let's say we have 5 watts EIRP, so we have 5 watts of radiated power from the isotropic radiator. We would have to have only 1.67 watts radiated power from the vertical. And again, as I mentioned, EIRP, similar to ERP on 60 meters, only we're referencing an isotropic radiator as opposed to a dipole. Now, we mathematically derive it in any number of ways, but the most common equations are taking the transmitter power output, multiplying it by the antenna efficiency and the antenna's gain. And for our purposes, we generally assume that the gain is 4.77 dBi, which is the perfect ground gain, which would have a factor of 3. That also goes for small loop antennas, which are about 4.82 dBi. The second equation, which if we have a different, if we measure different parameters, the power EIRP equals the current squared times the radiation resistance times the antenna gain. And yet another method, as defined in one of the FCC publications, is using the field strength, which is basically the electric field strength times the distance squared over 30. And this one is, that particular method is probably not going to be used much, and we'll go through why actually measuring field strength is generally impractical for the average ham. Now, some may ask why we use the perfect ground gain and whether we can actually use the real ground model numbers. You can, but various studies by King and Smith, and of course the famous Brown-Lewis-Epstein study, which formed a lot of the basis of the things they do in the broadcast industry, showed that ground characteristics at LF and lower MF are different from HF. And you can see in the graphs how in the left-hand one shows the conductivity and how it changes with frequency, and the second graph is the permittivity as it changes with frequency. So unless we actually make a ground measurement at 40 to 75 kilohertz, or try to extrapolate from measurements made at HF, try to extrapolate from the graphs an actual value, it's safer to use the perfect ground gain because it actually provides a theoretical limit that we can't exceed, and when used in our calculations will always keep us under the EIRP power limit. Now, some of the factors in calculating EIRP include radiation resistance. Anyone that's modeled antennas will be familiar with this. It basically relates the radiated power to the current. And it's not something we can actually measure directly, so it has to be derived from various methods, including modeling using EasyNet or Manigal. And just a note from N6LF, who's done a lot of study on the subject, the soil characteristics for frequencies under 1 megahertz are dominated by conductivity, so the radiation resistance of the actual antenna will be very close to the perfect ground model. So again, just like using perfect ground gain, when we model an antenna that we're thinking about trying out, we can stick to the perfect ground model. We can also derive the radiation resistance from equations. Most of the time, in simple cases where there's no top loading, once you start adding in top loading, the calculations get a lot more complicated. And again, N6LF has a lot of detail in his antenna notes online. Another method is spreadsheets. W0YSE has a spreadsheet that you can plug in numbers and dimensions available online, as well as online calculators, which are basically just forms. You plug in numbers and they'll spit out various parameters, including the radiation resistance. Feed point resistance, of course, if you've worked on antennas, that's another familiar quantity, which we can find with using antenna analyzers, keeping in mind for 630 meters that it has to be accurate and have coverage down to 475 kilohertz. Most of the rig expert analyzers will work down there. The MFJ 259B will, with some modifications to its oscillator. Keeping in mind with any analyzer that there could be effects from strong AM broadcasts. So in some cases you can use filtering, but we have to make sure that those aren't affecting the actual measured values. And of course, analyzers are the easiest method to measure the feed point resistance. Another method is an impedance bridge, like a General Radio 916A. But that requires external equipment and is generally requires a little more skill to get the right, to actually get the values. Another factor is the RF current. Of course, we can measure this with a standard thermocouple RF ammeter or any number of current transformer meters. W1TAG has examples. And we can measure the current on any side of the loading inductor. The reason for that is unless we have gross stray capacitance from the coil, the current is essentially equal. And of course, the third equation that I pointed out isn't really practical is field strength. And there's a lot of conditions to get an accurate measurement pointed out by W1FR. At 5 watts EIRP, at 500 meters out, which is about the minimum W1FR recommends, we only have 1.6 microwatts per meter squared. And cheap available field strength meters like the Heliogenosis EM2 only have a sensitivity of 50 microwatts per meter squared, so it's definitely not sensitive enough to make an accurate field strength measurement. Other tools could be a selective level meter, but that's another very elaborate procedure. So field strength measurement, generally speaking, is going to be out of reach for the average ham. Now, how important is efficiency on 630? And this is probably one of the more important things to take away. If we look at our, take our original EIRP equation and move factors around a little bit, we'll see that basically efficiency is inversely proportional to the transmitter power. And if we look at the graph on the right, we'll see that there's a point of diminishing returns after about 15 to 20%, where we're only reducing our transmitter power by a watt at a time at that point. So anything above about 15 to 20, again, probably not worth shooting for. And of course, the transmitter output power on the low end of efficiency can be increased to get us back up to 5 watts EIRP. But there are limitations on that end. Of course, we have the 500 watt FCC limit. The available power from most average amplifiers is under 150 watts. And the RF voltage at the base can get very, very high if you have a very low efficiency because of the high reactance. So good target is between 1 and 10%. And that may sound very low, but it's a very effective target range to shoot for. And that'll get us 5 watts EIRP with very respectable transmitter power output. There is a benefit to having low efficiency, and that is wider SWR bandwidth. So we don't have to retune the antenna as often, less wear and tear on tuning components. Of course, it's not the best way to increase the bandwidth. And as an example, 13% efficient vertical, these were measurements I took on my own antenna. The 1.25 to 1 bandwidth was only 54 hertz. Or I'm sorry, 540 hertz. Up to 2 to 1, it was only 2.36 kilohertz. So they're very narrow banded antennas. Next question would be, why not directional antennas? Well, what happens is when we start to add additional gain to an antenna, we have to then counter that gain with lower transmitter power. And as you can see in the illustrations, like the one on the right is a 4-square, as we're reducing power, we're not covering essentially the entire azimuthal 360 degrees. So we're actually we're actually losing potentially contacts. So we can see in this case a vertical is probably the optimal antenna to use on the band. The effective directivity, of course, a directive antenna is good on receive, but there's no sense in actually building a transmit receive antenna to benefit, a transmit antenna to reap the benefits on receive, because there's generally more costs involved, larger areas. An example would be, say, a full-size quarter-wave 4-square versus an 1/8 wave spaced 4-square using high impedance amplifiers, where we don't have to have top hats or radials or any other additions to actually make it resonant. Now, the types of transmit antennas will include, the majority will be vertical monopoles. We can get good efficiency. There's many variations that can fit almost any lot. And as mentioned before, they're the most effective to exploit the EIRP limit. Small loops are another alternative. They have much lower efficiency, but since they are ground independent to a certain point, and also are primarily the mag field is dominant in the near field, they're good for heavily wooded lots because of reduced near field losses. And we don't have to have a radio installation, so it's good for areas where you can't actually lay radials. Now, some people have tried dipoles, obviously not something that's recommended. At the low heights that they would be in terms of wavelength on 630, they act more like a small loop. They have even lower efficiency and are characterized by considerable ground reflection cancellation. There has been a station, W1IR in Vermont, that used some to some success, but of course he hasn't had any comparative examples, so the jury's still out on exactly how effective a dipole really is. So looking in more detail at the vertical, again, it's the most useful in terms of maximizing our radiated power. Ideally, it's omnidirectional and has minimal high-angle radiation. They're electrically short, usually under 1/10 of a wavelength because of that 60-meter, 197-foot limit. Radiation resistance is usually under an ohm, but we can certainly get higher radiation resistance with some effort. Naturally, they're a high reactance antenna, and of course, methods of reducing that reactance are with capacitive top loading, which can take on many geometries, T's, discs, umbrellas, inverted L's, very similar to the type of things that we build for 160. And of course, top loading will reduce the resonant frequency as well as increase the radiation resistance. We can also repurpose existing HF antennas on the property. We can take, example, a loop sky wire or a horizontal loop and actually short out, whether it's coax, the center conductor to the braid, or if it's ladder line, conductor to conductor. And essentially the feed line becomes the vertical radiator, and the horizontal loop part will become our top loading. And this can be used with any number of antennas, dipoles, inverted Vs, G5RVs. Or we can retune other low-frequency antennas, like, for instance, a 160 vertical or L, by adding inductance, changing the matching networks, or adding additional top loading. And there is an illustration here where you can actually feed a grounded tower. This was developed by N6LF by using a pair of coils and top loading off the top of the tower. Now, methods to resonate a short vertical would include having a coil in series with the vertical element, and this is the reactance of the coil cancels the antenna's capacitive reactance, and they can take on a number of forms, whether it be a fixed, tapped, or roller type inductor. Variometers are very common, where we're using a rotating coil inside a larger coil, or a sliding inner coil, which would be the bottom example by N1BUG on the right, actually has a sliding coil to vary the inductance. Other methods are slug-tuned or disc-tuned coils, which are common with NDB beacons, but it's a lossier method, not generally used by amateurs. And of course we can remotely tune if we have taps or use a motor for things like variometers and whatnot. If the antenna is long, so to speak, or is inductively reactive, we can use a series capacitor to cancel the reactance. And usually this will be a vacuum variable with fixed caps in parallel. Now, as far as the size of the inductor capacitor, we can measure the feed point with an analyzer to basically get the reactive component and just solve the simple equations to figure out how much inductance in most cases or capacitance we need. Another method is to use a fixed coil and a series variable. And in this method, we actually use a larger than necessary inductor and something like a vacuum cap in series with it to tune out the extra inductive reactance. And this is a method I use on my own antenna as well as K5DNL. Now, some basic rules about short verticals. As far as the vertical section goes, the higher you go, the higher the radiation resistance, and generally that's going to translate into higher efficiency. One thing to keep in mind that doesn't have to be perfectly vertical. N6LF actually modeled sloping down leads even out to 50 foot from where it would drop vertically, and it made very little difference in the antenna pattern or even the radiation resistance. So a key thing is don't worry about it sloping and make it as tall as possible. Capacitive top loading, some rules here. It's the most efficient method to basically load an antenna, a short antenna, versus say just using all inductive coil reactance cancellation at the base. And it increases the radiation resistance as well as the efficiency. Reduces the amount of coil, which in turn reduces coil losses, which are actually a big factor in our overall losses. They don't have to be symmetrical, but things like a flat top configuration are best. We can use sloping wires, but they generally shouldn't slope down more than 50% of the vertical, otherwise we'll have excessive cancellation, and our radiation resistance actually starts to decrease at that point. And for two-dimensional antennas, we can actually improve them by running parallel wires. They would be parallel on the horizontal plane and not one over another. And we'll have an example that actually shows why flat top versus vertically oriented parallel wires is more effective. And putting a skirt wire at the ends of, say, an umbrella or a spoked type of top hat will also increase or decrease the antenna's capacitive reactance. A rule of thumb for this is get as much wire in the air as possible. As far as loading coils, we want high Q with low loss forms, generally as large a conductor as possible. We want to keep them clear of any kind of conductive objects to reduce any kind of leakage or capacitive coupling, including ground. Generally, they're going to be cylindrical, single layer type coils. As far as placement in the circuit, they're almost always at the base of the antenna. As long as we have sufficient top loading, it really doesn't make that much of a difference to elevate it. And as far as the top of the coil, we want to use hardware that's rated for handling high voltages, because that's where we're going to see, in some cases, very high voltages or at least a peak voltage off the top of the coil. And N6LF has a very in-depth study of coils and increasing Q and various dimensions and form factors and whatnot. As far as ground systems go, the general rules would be get at least as long as the vertical section in any direction where there is not top loading. Put them under and extending from top loading wires. In cases where we're using something like an umbrella or a disc, we want to extend out generally about 25% from the top hat radius. As far as density, 50 plus on the ground is recommended, and 16 or more for elevated counterpoises. which is an option for restricted spaces. N6LF actually shows that if we can't get out to more than 50 feet with an on-ground radio, a raised counterpoise on 630 can actually be as effective. And for lack of wire, we want to concentrate as much as we can near the base, which of course is where the peak current is at. So that translates into using many short versus very few long ones. Conductor loss is not as big a deal, but generally speaking, if we want to try reducing them, doing so requires increasing the effective diameter, and that would include using, say, tubing or wire cage or even a tower. This generally involves the vertical section and not so much the top loading part, because again, a flat top loading situation is actually more effective with the same number of wires as opposed to rolling them up into a cage. Now, one of the dangers of 630 antennas is the high RF voltage at the top of the coil or at the ends of the top loading wires. So obviously keep clear of people, pets, trees. We need to use good insulators at these spots, like at the base of the actual vertical element. Good ones are glass and ceramic. Slightly less good, but acceptable would be something like Delrin or Teflon. PVC is definitely not recommended, and we'll see why in a minute. And this is all due to the high reactance. If we look at the equation, our voltage is essentially the product of current and the reactance, whether that's figured by the modeled reactance of the antenna or the reactance of the loading coil. Essentially, they all come out to be more or less equal. So the effects of the high voltage are insulator breakdown, coronal discharge, personal injury, or even fire. And so the point being, we want to try to reduce the reactance. And an example here would be a 30-meter high, 40-meter dipole fed as a T antenna. When we put enough power into the antenna to get 5 watts EIRP, we end up with about 5.3 kilovolts at the base of the antenna. And these are some examples of situations that have actually happened. We call it the Hall of Flame. And you can see lots of melting, burning. Even in one case, it looks like KL7L got ceramic hot enough to actually melt through a plastic tub. So these are all situations to try to avoid, and again, use good insulators if we can't get the reactance down enough. To match the feed point, we would use an un or an auto transformer. That's probably one of the more popular methods. Of course, to figure out the turns ratio is equal to the square root of the impedance ratio. Down at 630, 77 mixed cores are common, sometimes stacked, depending on the power levels that need handled. And we want to make sure on any side of, whether it's a primary or secondary, that we have at least twice the impedance, twice the winding impedance as the, or twice the winding reactance as the circuit impedance. What better is 5 to 10 times. So if we're working with, we're on the 50 ohm side, it would be advisable to have 250 to up to 500 ohms of winding reactance. The benefit of an un or an auto transformer, we have a DC ground circuit, so we'll keep static discharges to a minimum, or static discharged. It's a wideband solution, and it also provides galvanic separation between the feed line and the antenna. Also isolates the feed line from the counterpoise so it doesn't just become another radial. And generally we want to interweave the windings to get the best coupling. Other methods would include tap on the main coil. This is often done in mobile antennas, whether it's the main coil or a small coil between the bottom of the main tuning coil and ground. And there is some interaction when you're trying to change taps to find that 50 ohm point. You may have to change taps on the main tuning coil to get back to resonance. Other methods, inductive link coupling kind of harkens back to how we would have coupled our transmitter outputs in the old days. That's still applicable here. And also a shunt capacitor, which is basically a standard LC network. And the main tuning coil can actually be part or all of the inductance in the LC network. And that's a narrowband method, so something like an un may generally be preferred. Here's some examples of actual antennas and characteristics they have on 630. One that we can look at in particular is, say you have a 160 inverted L 50-foot vertical. You would need about 450 microhenries of inductance, and even with a high feed point resistance of 40 ohms, which would be pretty high losses, we can still achieve about 1.5%, which, remembering back, that's within our acceptable range, and we would need about 111 watts of transmitter power, which again is a reasonable amplifier to build. An 80-meter horizontal loop at 40-foot high is actually, compared to the other examples, a very decent antenna. We can achieve a similar efficiency as the 160 inverted L, about 1.3, 128 watts in to get the 5 watts ERIP. And we can see that the base voltage is about a kilovolt, and that's still manageable, and we only need about 200 microhenries of tuning inductance. And looking at an extreme example would be a 30-foot high 40-meter dipole. In this case, we need about 650 microhenries of inductance. And if we put enough power into the antenna to get the maximum EIRP limit, we'll be looking at about 5.3 kilovolts at the base. So again, that's something to consider in short, very highly reactive antennas. Now, as I pointed out before, we can make some improvements. In this case, we're taking an 80-meter dipole at 35 feet and just simply adding a parallel wire to it in the horizontal plane. And by doing so, we drop the required inductance by almost, by 120 microhenries and reduce the base voltage by nearly a kilovolt. So we're reducing the amount of inductance we need, which, as mentioned before, will reduce the losses involved with the inductor, and that'll improve efficiency. And another effect to adding that second wire on each side is the 80-meter antenna can become more broadbanded, especially if we use, say, one set of wires tuned to the lower part of the band and the other set of wires tuned to the upper part. Now, loop antennas are another alternative. They're generally less than a wavelength in perimeter in any kind of closed shape. The radiation resistance depends on the amount of area enclosed. So we can have different shapes, but we want to basically try to maximize the area within the loop, because that's the radiation resistance usually in the milliohm range instead of being approaching 1 ohm like a vertical would. Efficiencies are typically below 3%. N6LF cited that there is a limit of about 4.2%. The current is uniformly distributed, so it doesn't really matter where we feed it. We're still going to have vertical polarization as long as the plane of the wires is in the vertical plane. And the radiation pattern is actually different than its larger than one wavelength cousin, where we actually have peak radiation in the plane of the loop, as opposed to being perpendicular like the larger one wavelength or larger loop. But we do notice that there's lots of high angle radiation, so the takeaway from this would be it's not the most effective use of our radiated power, because we're putting power at high angles, and we also have these nulls along the azimuthal. Now, they have high current, so we want to generally use larger inductors. That could be multiple wires or even something like lits, coax. The magnetic field, as mentioned before, dominates in the near field, so we have much less environmental loss. There was actually an article in QST in February that dealt with the effects of live trees on HF antennas. Ground system's not necessarily required, but it actually will benefit and decrease some of the near field losses. And to resonate it, we would use a series capacitance. Of course, it has to be rated for the RF voltages and current involved. Something with low ESR, like a vacuum variable. And as far as matching, we can go back to the UNUN with 77 cores, or ON7YD shows an example here of using a back-to-back C network. And this is just an example of basically a loop circuit by W1TAG. And he has the additional components added in a current sensing transformer to actually take RF current measurements. And there are some experimental antennas out there. How well they work is still out for debate, but VK4YB has done some experimentation on things like a voltage-fed linearly loaded vertical. You can see that in the illustration at the bottom. He's actually feeding it at a high impedance point and running the wire up to 120 feet up in a tree, dropping it vertically, and then running basically the loading wire down along the ground 10 feet above ground. And this actually brings a current up to the middle of the vertical portion. And then he just uses a link-coupled tuner in the shack on the high impedance side. And there is no loading coil. Basically, you tune it to resonance by trimming the linear loading wire along the ground. And it's a similar concept. He has a bottom hat antenna, which is like an inverted L, but the end drops down and then tees out. And you can basically trim it to resonance by adjusting that T. And it may be a little bit counterintuitive because the currents will cancel to some degree, but because of the distance of that far end drop from the actual main vertical, it's actually not as big as cancellation as we would assume. And of course, there's other kinds of experimental ones, and the band being a very experimental band in nature, there's obviously other designs out there unexplored, possibly something like a K2AV folded counterpoise, which gained some popularity on 160 antenna installations. So I would suggest anyone that likes to experiment can make their own contributions in any number of ways with new experimental antennas. Now, my own personal antenna is a 67-foot aluminum tubing vertical with 8 top-loading wires. To keep away from troubles with high voltage, I use a glass beer bottle as an insulator. And it shares 22,000 feet of radials with my 164 square. It has about 13% efficiency and uses a 9-to-1 UNUN for feed point matching with 77 cores. And as I mentioned before, it uses the method of using a larger than necessary inductor and tuning it back to resonance with a vacuum capacitor. And any recommended reading would be N6LF's antenna notes. He's gone into great detail. So there's a lot of good material there to get a deeper understanding of some of the concepts. ON7YD also has an excellent page on 2200 meter antennas, but of course a lot of that information can be adapted to 630. All right, so now we move on to receive antennas, and we ask why do we want to use receive antennas? And the name of the game here is nothing more than improving the signal-to-noise ratio. Otherwise, we could just use our transmit antenna. And again, we pointed out directional transmit arrays really don't make any sense from a financial or a material point of view. So we can use any number of smaller and more effective receive-specific arrays. And this is where the biggest rewards come, is improving your receive capabilities, because we're all limited to 5 watts EIRP. So regardless of how big an antenna you can put in, the difference between how effective a particular station can be is how effective its receive antennas are and its receive capabilities. By improving SNR, obviously, we improve the quality of or quantity of our contacts. That means more DX, or digging signals deeper in the noise, dealing with QSB better. If you like to rag chew, we can have more consistent and sustainable rag chewing. Now, ways to improve it, one misnomer is by increasing gain or efficiency, and in this case, neither one will actually help us to improve SNR, and we'll see some methods that actually will improve it. Gain only has to be sufficient to exceed the system noise, which would include any kind of noise introduced by amplifiers, the receiver itself. Anything down to about -18 to -20 dBi we can accept without having to use a low noise preamplifier. Anything below that, generally, then we'd want to use a preamp. And actually, reduced efficiency can be used to our benefit when we're talking about phased arrays, because it actually reduces phase excursions by the SWR bandwidth is widened, which will reduce phase excursions in arrays where accurate phasing is important for directivity and whatnot. Of course, we have to identify what kind of noise we have to discriminate against, whether it's propagated or locally generated, and this is going to affect the methods we use to mitigate those. It could be through antenna nulls, which will discriminate against, say, local man-made sources in the far field or propagated noise in the far field. Directivity, which will discriminate against evenly distributed noise that's propagated, and of course in the far field, away from the direction of the main lobe. And for directivity, we quantify it with something called RDF, which we'll look at in a second. As far as near field mitigation, the most effective, well, pretty much the only effective other than eliminating the source, because the antenna pattern hasn't developed, is through noise cancellation, and that's using something like an NCC, well, now it's the NCC2, or say like the MFJ 1026, to actually phase out local noise sources using a noise sensing antenna placed close to the noise. Now, keeping in mind the name of the game is to improve SNR, we also have to avoid degrading the SNR, maybe through careless construction or things like that. One big one is common mode noise. We have to make sure that we're properly choking the feed line, and that's commonly done with BN 73202 cores. Anyone that's put together a beverage, I'm sure, has wound one of these. To get an adequate amount of choking impedance on 630, we often stack them end to end, which will increase the inductance and obviously the choking impedance. Another one is station bonding, making sure we don't have any voltage differentials. K9YC has a nice tutorial on that. Antenna location is another way to avoid degrading SNR. We can actually move the receive antenna to a so-called quiet spot outside certain near field source, or the near field of certain sources, which is a lot easier to do and move around than a transmit antenna. And of course, separation from a transmit antenna. If we can't get out to more than a half or a quarter to a half a wavelength, then we probably want to look into some kind of detuning method, and there's various examples off in the right-hand margin. Now, how do receive antennas compare between 630 and 160? The near field is obviously larger, so we'll be more susceptible to a greater number of local interference sources. Antennas are generally physically larger to maintain the same kind of directivity. That would include beverages are longer, phased arrays have wider spacing. Exceptions to this would be things like terminated loops, verticals, or magnetic loops, where the pattern stays the same but results in lower gain. Choking impedances are higher, and antenna gains are generally lower, but we can tolerate them because essentially the ambient noise on 630, as we pointed out before, is a lot higher than 160. Except in very quiet rural locations. Now, we mentioned something called received directivity factor, and this was something promoted by W8JI. Essentially, all it is taking the the gain at any given point in the antenna's pattern and subtracting the average gain of the antenna, which is something that is calculated by EasyNet. Now, this is somewhat of an arbitrary value, so if you're comparing antennas, you really have to define a certain elevation angle, because if you change the elevation angle between different antennas, or even change the elevation angle amongst the same antenna, you'll get a different RDF value. So it really does require, if you want to make accurate comparisons, to pick a certain elevation angle. Generally, it's somewhere between 20 and 35 degrees, 25 being most common. And we look at how antennas rank as far as RDF. We see things like, ferrite rod and coil, kind of unknown. I didn't really have a convenient method to model that, but verticals and E-probes are about 5 dB RDF. We go up through like the small loop antennas, a half-wave beverage. We actually see that an EWE or a Pennant is an improvement over half-wave beverage. Then there's the shared apex loop that's gained popularity recently. And then things like phase verticals, one-wave beverage. As we're moving up, we get into things like four squares, longer beverages, and then at the high end of the RDF range are very large phased arrays like a high Z phased 8 circle or a broadside end fire type of circular array. So the type of receive antennas could range, say, from something like a haphazard antenna. This could be your HF dipole or anything you have around. Now, they may improve the SNR, but generally it's unpredictable and is just incidental. So it's not really recommended to use a haphazard type of antenna for receive. We really want to use something that some thought has been put into maximizing directivity or nulls or any number of things we mentioned previously to improve our SNR instead of just having something happen by accident. Now, verticals and E-probes in and of themselves are not much of an improvement over a transmit vertical. Now, any observation, some people have observed that maybe an E-probe actually has a better SNR, and usually these may be a result of the location of the antenna to sources in the near field. Again, it's easier to move a small receive vertical than it is a large transmit vertical and all of its associated top loading and ground radials. Or it could be common mode differences, where we may have adequate choking impedance on the receive vertical, but not on the transmit vertical. They're also the optimum elements for phased arrays because they're compact, small space requirements, and as far as high impedance ones that use amplifiers, we don't require any radials or top loading and whatnot. And of types of radials, we can use a resonant passive vertical. It's actually basically a miniature transmit vertical. Some operators are using what's called a non-resonant low noise vertical, just basically a short vertical element, no top loading. There are ground radials, but we have a 10-to-1 step-down transformer and use a twisted pair balanced line or even Cat5 back to the shack and a 1-to-1 isolation transformer with a preamplifier. And again, they do require a counterpoise. Then we get into what probably a lot of people are familiar with is the high impedance or active verticals. And they're basically just a whip element, or in some cases just a plate using high impedance amplifiers like the high Z's, the YCC ones that you can get from DX Engineering, or we can use higher gain ones, which commonly go along with the term E-probe. And those would include ones developed by PA0RD, W1VD, or even homebrew amplifiers centered around like the J13 transistor. And again, these are shorter elements or a plate. And we typically feed the power through the coax. So we have a 1-to-1 isolation transformer at the antenna end and a bias T or something like that at the receiver end of the feed line, or even an isolated transformer, isolated winding transformer could be used. These don't require any radials, just basically a ground reference rod or a pole or stake. So very minimal installation requirements. Oh, and the other benefit is they have a wide, consistent impedance, which, as we pointed out before, with the widening of the SWR bandwidth, minimizes our phase excursions. Ferrite rod's not that useful. You see that in portable receivers most of the time. Small loops are similar to their transmit counterparts. RDF is pretty low, about 5 to 6, so we can look at alternatives. Generally, these are rotatable. The shared apex is an improvement in RDF, and actually, as I said, gaining popularity on 160 and whatnot. And there is an alternative for LF and MF with a larger footprint. Now, looking at terminated loops, these include things like a K9AYEWE. They have a respectable RDF that's actually better than a half-wave beverage. And on 630 meters, in most installations, that's about all we can get out to on as far as beverages go, which would be about 1,000 feet. If you can go longer, definitely do it, but if you can't go any longer than 1,000 foot, then we want to use something like a terminated loop. And these are good, of course, for small lots. Space requirements aren't too high. This is an example of one used by WA3TTS. I'm not going to go into too much detail, but he has, it's a very effective antenna. He lives just outside of Pittsburgh and has done very well both on DX to Europe and across the country in receiving. So it can be a very, very effective antenna. Also, W7IUV has used rotatable flag that has shown very positive results. W1VD has done some modifications to a K9AY. And as we mentioned before, beverages probably aren't too practical unless you can get out further than half a wavelength, which would be more than 1,000 feet. And we'll, am I running a little? Okay. Well, we'll try to wind up here, but bogs are another alternative, especially over poor ground. They tend to be much shorter because of the velocity factor near the ground than other overground counterparts. So we could actually get away with a 550-foot bog as opposed to having, something like 1,000 or 2,000 foot above ground beverage. So bogs are definitely an alternative. Now there's a lot of things to be careful with as far as installation and how to maximize the performance. So it very much requires experimentation and starting long and cutting backwards until we see the best front to back ratio. And then of course we have phased arrays. These are really the most effective type of antennas, which could be composed of verticals or terminated loops, or even arrays of beverages, which on 630 are probably not too practical. We can use different phasing schemes, broad fire, end fire, or a combination of the two. And we can even generate or create steerable arrays if we have the right geometries, which would include triangles, four squares, or even circular arrays. And as far as realistic RDF ranges, we can have anything from about 9 dB up to, as we pointed out, something like a high Z would be all the way up to 13.5 or 13.4. These are just various patterns. Let's see. We can see that we still have some effective patterns with broadside. We get a lot more front to back with end fire type examples. If we start to combine them, we can see the patterns starting to narrow and really show some benefit. And let's see here. As far as, I just wanted to touch on an actual example. This is an example. One of my best receive antennas is actually a full-sized 630 meter 8 circle. It's approximately 1,140 feet in diameter, or has 1,140 feet broadside spacing and 470 feet end fire. The total space that it would fit into is about 30 acres. So it's a pretty large antenna. The bulk materials, just in the RG6 phasing lines and delay cables, came out to about 5,900 feet of cable. And then, of course, about 190 feet in aluminum tubing for the elements. The RDF is somewhere about 12.5 with a half beam width of about 55 degrees. Probably very close to, I'd say, like a 3-element Yagi on 160 as far as receiving goes. And the front to back has been observed to be upwards of about 25 dB. And this just originally used tuned resonant elements, but I eventually switched over to high impedance elements just to simplify the installation. Didn't need radials anymore, top loading, and of course the phase, to reduce phase excursions because of the constant feed point impedance presented by the high Z amplifiers. And it's using a switching array that W9RE came up with to do the broadside end fire phasing. And we can see an example here of its actual performance. WD2XSH7 in Louisiana was dog boning on CW looking southwest, but as we look about 3/4 of the way into the waterfall there, heading towards the right, when we switched to northeast, he all but disappeared. And we can see the next station below that, WG2XKA in Vermont, of course, came way out of the noise as opposed to almost being non-existent to the southwest. So as I mentioned, improvements was going to high Z amplifiers, and that eliminated a lot of problems with deer or other wildlife pulling radials up or knocking top loading wires down. The only further improvement to something like that would be going to an actual high Z type of phasing scheme, which all 8 elements are active in kind of a triangular phasing with plus 106, minus 106, and 0 degrees. And it actually does, using that scheme, result in a smaller diameter array of only about 800 feet. So the last thing I would say as far as receive antennas, these would be my picks. They're kind of the bottom line based on your lot size. If you have a 100 by 100 foot lot or less, something like orthogonal reversible EWEs using the WA3 TTS dimensions, a K9AY using W1VD dimensions, or even a shared apex loop. For lots up to about 200 by 200 foot, a 16th wave 4 square would be a good idea, though when you start to get that small phase, trying to keep the phase relationships accurate gets pretty tricky, and you have to be careful, and that could use active or passive elements. 300 by 300 foot lot, we could use an eighth 4 square, which is less critical as far as the phasing. And anything over about 800 feet definitely would go with an 8 circle, whether that be a broadside end fire or a high Z type. So I'd like to thank KB5NJD, K9YC, WA3TTS, N6LF, and W3LPL for reviewing and providing a lot of inspiration and just having a lot of these guys active and promoting the band, and hopefully we'll see a lot of you guys on the band in the future. So thank you very much for your attention. Thanks a lot.
Thank you. The slide deck that you just saw from Eric will be available on my website, www.k3lr.com, here in the next few weeks. So for those of you who want to learn some of the intricate details, you can make sure that you go there. Our next presenter, the title of the talk is Near Vertical Incidence Skywave Antenna System Design, Construction, and Operation. Please welcome Corey Gibson, W3CDG.
Good afternoon, everyone. How's everybody doing? Enjoying the Hamfest so far? Good. All right, we'll give you a little talk about NVIS. What is it? I get a lot of questions. It's, these letters, NVIS, what does that mean? Well, we'll get into it here and give you an idea of what it comes up. what does it mean? Near vertical incident skywave. This is a radio signal that has a high takeoff angle. Generally, when you're trying to work DX, you don't want to shoot your signal straight up in the air. You want to send it out and have it bounce. You want to throw a football long, you don't throw it straight up in the air. It's not going very far. You want to throw it out. This is a radio signal, has that high takeoff angle, and it gives you a very reliable 200 to 300 mile coverage. Sometimes that range can be greater, it kind of depends on conditions, but in general it's found to be pretty reliable in that 200 to 300 mile area. What's this good for? Well, QSO parties, great for the PA, Ohio, different QSO parties because you want to get the guys in your state. Also great for emergency communications. You know, trying to get into a situation, you want something fast, you want something portable, you don't necessarily need to get your signal all the way to California from Ohio, you need to get it out of the effective zone, whatever that is. And 200 to 300 miles usually get you where you need to go. Some of the advantages of NVIS, you know, this NVIS antenna, NVIS operating technique, you know, way of propagation, it can cover an area greater than ground wave. So if you guys get on a ground wave net, you know, the further away you go, you get your antenna up higher, you try and get that signal out. Works okay, but starts fading off pretty quick. You know, since we're using a high takeoff angle, we're shooting the antenna straight up into the air, we're bouncing it off, coming down. One of the things they talk about is basically like take a fire hose, spray it at the ceiling. Where does the water go? All around you. So that's where we've got. Since we're using these very high takeoff angles, you know, terrain isn't as much of a concern. Emergency communications, you know, you've got to put your repeater, you try and put it up on a hillside, trying to put it up on top of a mountain, you know, because you want to cover as much as you can. If you have something in the way, you know, our county, Mercer County, Pennsylvania, has a ridge runs right up through north to south. Great coverage on one side, great coverage on the other, but getting over the ridge with 2 meters can sometimes be tricky. Well, how do we get over that? We shoot the signal up, bounce it off the ionosphere, and bring it down on the other side of that ridge. So we don't need to worry about the terrain as much. You're down in a valley, you know, you have an area, there's, you know, an effect down in a hole somewhere, can't get coverage. NVIS, you know, once again, shoot the signal straight up in the air, comes down all around you, so you don't have to worry about it. You can go a lot further without a repeater or other infrastructure. You know, small antenna, a radio, and you can get that signal out a couple hundred miles. Another thing about it is the antenna setup. The antenna setup's fairly easy. You know, when you're trying to set up for field day, you've got guys with bows and arrows trying to get the antennas into the tree and people running for cover. You know, you want to get that antenna as high as you can to get that signal out further. You know, in this situation, you don't need to. 15 to 30 feet works really well. I mean, I threw, first NVIS antenna I did, I had a tennis ball with a piece of string. I threw it up over a tree branch, strung the 80-meter dipole out, and away we went. You know, we don't need to get that antenna quite as high. Helps, you know, quick setups with that. All right. Why does NVIS work? What are we doing? Why does this work like this? You know, what frequencies do you want to use when you're using NVIS? There's a lot of different things, but you know, usually 80, 40 meters is probably your best bet. Sometimes you can get on 30, those work. You know, you've got your limitations there on 30 with digital modes. You know, 60 meters, things like that, you've got channelization. So 80 and 40 are the best, and why is that? Well, during the day, you know, the E layer is densely ionized. Sun heats up, ionizes that E layer, and the F layer gets it good and going for propagation. The MUF, the maximum usable frequency of that, is usually around 10 megahertz. So we got to keep our signal under 10 megahertz, or the signal just goes off into space and doesn't go anywhere. It doesn't refract anything over 10 megahertz. So 10 meters isn't going to work as well, you know, things like that. So with that being at 10 megahertz, this will allow that refraction to occur. However, during the day, that D layer, sun also builds up that nice D layer for us. That absorbs most signals over 4 megahertz, or under 4 megahertz. So you're on 80 meters, you key up, signal goes up, gets absorbed into the D layer. Doesn't do us much good. All right, we'll key up on 40 meters. Well, we're greater than 4 megahertz, so we can pass through that D layer, but we're under the maximum usable frequency of the E and the F layers, so we can refract the signal. That's why during the day, generally, you want to switch to 40 meters for NVIS. On our emergency communication nets, we have two frequencies. We have an 80 meter frequency and we have a 40 meter frequency. And because sometimes in the day you want to use one, night you want to use the other based on what's going on. So during the day, we use 40 meters. After sunset, the maximum usable frequency of the E and the F layers can drop, oftentimes below the 40 meter band due to the loss of the sun and the primary source of the ionization. But the nice thing for us that happens is the D layer also disappears. So now maximum usable frequency drops to 4 megahertz, but the D layer is gone. Our 80 meter signal, 3.5 megahertz goes up, no D layer, refracts, and comes back down. So that's kind of, people always ask me, why do you want to use what? And you read the things and they're like, 80, 40, this is when. To me, I like to know why, and it's like kind of an understanding of what can come out with that. Neat thing on this, when we do some emergency communication nets, we have a time change, right? We go into daylight savings time. It is absolutely amazing as you hit into the summer months and it's light earlier, how the 80 meter band starts dropping down quick. And I mean, if you guys are doing DX, you see the same thing in DX. The propagation on this is identical. The only difference is where you're sending your signal. Instead of sending it out, you send it straight up and drop it right back down on top of you. So, what kind of antennas? What kind of antennas do you want to use for NVIS? There are a lot of antennas you can use. My test bed, my standard antenna, 80 meter dipole, 15 feet off the ground, 15 to 30 feet. And that's kind of what you use as my standard. This is what we're going to compare things to. But putting up wires, sometimes you don't have trees. Sometimes you don't have a way of getting that dipole 30 feet up. You're out in the middle of a field. What are you going to do? So I said, well, let's model something. Let's look on a different type of antenna that doesn't require any trees. It doesn't require that support system. So we looked at this and been modeling and trying to focus everything right now on a loaded inverted V. Pros and cons, and we'll get into that. What this antenna consists of, we've got the model, is a full-size 40 meter dipole. So you've got your 60-some feet dipole with a about a 15-foot mast. So the top of the dipole is up about 15 feet. The legs come down. The bottom of the legs are about 3 feet off the ground, and that gives you your 40 meter legs. Originally, I did this with a full-size 80 meter dipole on top. So this antenna took about a 50 by 150 foot plot of land. Same thing, 15 feet at the top, down to about 3 feet at the bottom. But, works great if you have a yard, but some guys don't have that much room. So let's load the coil. Let's put some coils in there and try and shorten this antenna up. Design goal, let's make the antenna 50 feet square when it's on the ground. Take up a footprint of about 50 feet. So we've got the full-size 40 meter legs, center-loaded 80 meter legs of approximately the same length, trying to keep things based on where you're tuning and where you want them. So here's some photos of the antenna and what it's built. You've got the 15-foot mast at the top. The top, you've got a 1-to-1 current balun. This is a resonant antenna. There's some other designs for NVIS antennas that require a tuner. On 80 and 40, this antenna is resonant, so you don't need a tuner. Pros of this antenna, like I said, it's a small footprint. It's fairly easy to deploy. I've done it by myself, but with two people, you run up the fiberglass mast with a couple hose clamps, hold it, while the other person stakes out the four ends and the antenna's up. It takes longer to roll out the coax than it does to actually put the antenna up. The insulators are about 3 feet off the ground, to try and minimize some of the ground losses. Of course, anytime you get down near the ground, your antenna is going to react with it. In this case, the antenna is the actual support. You don't need additional guy wires. So you run this thing up, the antenna wire, and then that's what holds everything up for you. You don't need any trees to hold it up. Ready to go out in the yard. So you see it out in the yard there. It's about a 50-foot square. Got it near a metal fence. Does that affect it? Yes, it does, but it still works, still gets you on the air. There's things you can do with it. Some of the cons of this, obviously, there's no free lunch in amateur radio, and there's no free lunch in physics. The antenna wants full-size antenna. You've got your resonance. When you put a coil in there, you're doing a compromise. you're gaining space, you have to give something up. What do you give up? You give up the bandwidth. Full-size antenna has a little bit higher bandwidth than this one. The coil brings that bandwidth in a little bit. So we'll go into that. I've got some of the models. You can see what the bandwidth does and where it puts it. But what I think is kind of interesting is, they said no free lunch. Build a coil. I want to make this antenna, each leg, so much shorter. How much wire is in that coil? About what you shortened it. You've got that to make it run. You still need that much wire to have it work. So a couple of the models, this kind of gives you an idea of what we're looking at. So I took this exact antenna that we built out on the ground, and on the right-hand side of the screen, that's the NVIS. That's with it 15 feet at the top, 30 feet at the bottom. As you can see, we've got a 90-degree takeoff angle. Most of your energy is going straight up. Pretty wide, so you get a little bit of coverage, which is what gets you out that 200 to 300 miles. You got about 138-degree beam width going out. So that's what gets you your signal out a little bit further. Take that same antenna, move the model up, say, all right, we're going to move this up to a quarter wavelength. And you get the graph on the left, which is basically, looks like a pretty good DX antenna, 27-degree beam width and 21-degree takeoff angle. It's not a bad antenna for that. So, it's a way of moving your antenna. Move that antenna closer to the ground, and that radiation just starts going up into the air. Some of it goes into the ground, but it goes up into the air as well. So we look at the models. First thing you do when you're designing an antenna is you want to run models. Why? Well, it gives you an idea if you're even in the ballpark. They're not always perfect, but they're in the ballpark. Well, the model showed this was going to have a 3-to-1 SWR across the entire 40-meter band. All right, the internal tuners in most of the radios. I have an IC 7300. I can pull this anywhere on 40 meters, tune it up, and it works great. And we'll show what the actual sweeps end up here in a second. Like I said, on 80 meters, being loaded makes it a compromise. The bandwidth for this antenna is coming out to about 140 kilohertz. So it's a decent chunk of the band. That's a 3-to-1 bandwidth now. So that's what, I'm using that because that's what most internal tuners can handle. If you have a frequency that your ECOM group works on, tune it to that frequency, and then if you need to move off, you can. So that's what it comes out to be. Well, we build the antenna, we get it set up, we put it up in the air. What do we get? How do we end up? Well, once again, 40 meters was 3-to-1 across the entire band. It matched the model really well. Actually, it was 2-to-1 across the band, but I have a feeling that has to do with some of the facts that EasyNIC that I have the NEC2 model. I don't use the NEC4. It doesn't model the ground losses quite as well. So probably a lot of that, it looks better because I've got more loss. But it does match the model. On the 80 meter, I actually tuned it higher. Our net frequency is 3990.5, so it's all the way up on the top end of that band. So I didn't want to leave it right where I had the model set up. I just shortened the antenna and moved the resonance point up there so I could get it where I needed it. And I always say it on this, it's my favorite part. When you design something, you've got these models. It's nice when the math works out and you build it. Yep, that's right. It kind of verifies what you were looking for. So, like I said, on the 80 meters, we've got that coil. What's that coil doing? Well, one, it brings our bandwidth in. Two, it also creates some loss. What are we doing about loss? How much loss do we have in these coils? What's going on there? Well, the model shows it's kind of nice. You've got the thing here tuned to 39.1 megahertz. You've got basically putting 100 watts into a 50 ohm system, 1.01 to 1. The impedance is 50 minus J 0.4 ohms. So we've got a pretty good match for the model. So what are we doing on the loads? Each load's pulling out about 7 watts. So we're burning about 7 watts in each coil, which is about 15 watts across, total out of that 100 watts, or 0.7 dB. Less than an S unit, not something you really notice. When I AB the full-size dipole at 30 feet compared to this, yeah, I can kind of hear something, but not really a whole lot of difference in the thing. So we've got this antenna. What can we expect to our coverage area to look like? Well, I'm currently in Portage County, Ohio. So here's two circles on the map centered on Portage County, Ohio, 200 miles and 300 miles. As you can see, the 300 mile from where my location covers all of Ohio, most of Pennsylvania. When I lived about 40 miles to the east in Pennsylvania, I used this on the PA-QSO party, and I mean, it was great. I got all of Pennsylvania, just you can work everybody you can in there. And the coverage on this, we do our emergency communication nets Saturday and Sunday, local nets where we go out, each county has a roll call, and we find this to be fairly reliable. I mean, I pretty much, you'll hear net control, they'll be asking for, repeats, and I'm like, well, I heard them, and they can hear me, so works pretty well. Got a couple examples here just showing, what happens at distance, as you get out further, and switching it and A-Bing this with a vertical antenna. So first guy got on our net and he was using a vertical, nobody could hear him, switched to an NVIS type antenna, we can hear him. Well, why? Well, the vertical's shooting that signal, it bounces and skips right over the person. You're in the skip zone. You're past ground wave and you haven't hit the first hop, you're not going to hear him or you're going to be really quiet. So one way to do this, I was using FT8. I don't know if you guys have been using FT8, but it's a pretty neat mode and it's great. I can leave the computer run and just collect data, collect receiving data, not even, you can do some transmitting data as well. So here is on 40 meters, switching between two antennas. If you look, the time differential, there's like 1 or 2 hops, but there's one, I was trying to hit the same station, so there's a 30-second gap between these. So propagation shouldn't change much. Sometimes it can change in 30 seconds, but this was pretty reliable. This was a 411-mile hop down to KN4 DUF. I've heard him. On the NVIS, he was coming in about -3 on the signal to noise. And when I flipped over to a vertical to the BTV, 6 BTV, he was +1, so he had a stronger signal coming in. Okay, so the NVIS was a little bit worse in that respect. And I have a couple examples of that where, I tried to get some of these where I was listening further, but it was, I don't stay up late enough to hear the West Coast around here. I'm an early bird. Here's another one, 439 miles. They were close. They were really close. This was a pretty strong signal. The BTV came in at a +10, and the NVIS was a +8. A little bit close, not great. A little bit lower on the NVIS. Now here's where it gets funny. So that's kind of almost at the limit. That's just past of where we would expect the NVIS to work. I heard I1 BEP on the NVIS. He came in at -24. I mean, right. If you guys do FT8, -24 is the bottom of the barrel. Everybody that they think they can hear is dumped into that bucket, into the -24 bucket. And so he was coming in on the NVIS pretty consistently right at the bottom. Sometimes I wouldn't even hear him. Flip it over to the BTV, he was a -16. That's a little bit different improvement, and it's because of the way the signals are getting bounced with those antennas. One final example, basically, this was more of where the NVIS shines. Here we've got a 270-mile contact, 271-mile contact. I was listening to the single sideband, the Wolverine. Anybody here from the Wolverine net in Michigan? I was listening to the net one night on 80 meters, and I was listening to the net control operator. From what I can tell, he's about 271 miles away. So let's see if this video should play. I don't know if I need to plug it in. We'll try it. See what happens. I don't think the video is going to play. Oh, here we go. So 271 miles. Oh. Back it up there. Is this for the... Is it this one, Tim? Maybe? All right, so... Over to the NVIS. And now he's 18 over. So, I mean, you know, where the Hustler's pulling him in here, the NVIS is pulling him about 18 dB higher, which is a little bit nicer there. And I can't get rid of this now. I'll unplug it. All right. Yeah, I can't get that to come up over the speaker, so. But yeah, it's pretty neat. And I mean, you know, we use this pretty reliably on the Sunday morning nets for NVIS. You know, PA QSO party, Ohio QSO party. Great for parks on the air. You know, you want to get some of that stuff set up. Works out pretty well. That's all we've got.
Thank you, Corey.
So Corey's slide deck along with the audio will be on the K3LR website as well. And you can also find the other slide decks and all the way back to 2004 on the K3LR website as well. Let's see here. Some more of this. Oh, gosh. Yeah, I don't know how to get out of that either.
Yeah, it's like that won't go away. Do a quick reboot.
Yeah. Well, patience with us while we reboot. And
So now they plug. I thought this was with the.
yeah, we get it. Anybody have any questions on NVIS for Corey? Corey, come on up. We'll do some Q&A while we're there.
Yes. No, when you look at the azimuth, I mean, pretty much when you bring it down to the ground like that, it's just a cone straight up into the air. So yeah, I'm not, you know, on your azimuth pattern, you don't really see, it's pretty much a perfect circle. So right, but that it all goes straight up, and then when it gets bounced back down, it's all over the place. So. I can't hear. What was that? I can't hear you. No, I don't have one over there. We just got. They actually, we are selling them at DX Engineering now. It's like a design that we made. You know, I mean, I think I ran the quote. I think they're about 27 microhenries is what they need to be. So if that's what you're looking for.
Now to get stuck.
Stick, yep.
Lost that.
No, I think when you go into it, you do the, which one is next?
Next is
SSD.
yeah.
When you bring it up and you start the slideshow, it'll come over here, because that's the second, looks like the second monitor.
There was a control F70. Yeah, it's not going to come up. I think we're going to be okay here. I can't see the.
When you do,
no, it doesn't work.
oh, it doesn't?
I need. Can you see where?
Yeah.
It's got that.
There it is.
All right, the title of our next talk is Hydro Excavation for Radio Antenna Tower Construction. Please welcome Everett Jackson, WZ8P.
What do I hit? Oh, okay. Just the up arrow, Tim? Just the up? It didn't go up. How about page up? I hit the up arrow. Okay. Page up. Nothing, still didn't. Which one? Spacebar. Okay, thank you. Good afternoon. I am Everett Jackson, Whiskey Zulu 8 Papa. What do you see? A very, very nice place for a tower, right? Depends on who you're talking to. My wife didn't think so. However, she says you can build anything you want as long as it doesn't have any more of those guy wires. I said, okay, if I can have anything I want as long as it doesn't have guy wires, then let's see what we can come up with. Well, here's a nice tower. We built this one by the barn. It's 10 feet square at the base and 4 feet deep. I took the measurements to build the tower and called in to the concrete company and told them how many yards of concrete I needed. And they said, well, okay, we'll send it out. So they sent a truck out, and we only got the hole half filled, and we ran out of concrete. And I said to the guy, where's the rest of it? You got another truck coming? He says, no. I said, well, why didn't you send me more? He says, we didn't think you had your measurements correct. So basically, you can see I have a barn here and a generator, 25 kilowatt generator, and that is Roan SSV, freestanding tower. It's 120 feet tall. Starts out with a 6 at the bottom, 6, 5, 4, 3, 2, 1. Fortunately, I put all my ropes at the top of the tower before we put it up, because once you get this Roan 6 through 1, you can't climb up on 1 very, very well. It's very, very small. Only 2 people have ever been up the top of that tower since it's been up. So you can see here that if you're going to build a freestanding self-supporting tower, you need to decide how you're going to use it. I use this one for 80-meter dipoles and to hold up my full-size 80-meter beam on Europe with 4 elements on a 140-foot boom. So this is where it starts. Continuing on, if you're going to build something, you got to get some instruction, right? So the Roan book is a very good place to go to get the instruction, or talk to some old geezers who have done this before. So coming for 48 years to Dayton, I've talked to a lot of people about how to do things. The worst advice I ever got was, when you bury your cable underground, put it in pipe, run it into the basement, and run it into a box. That sounds good. But then they said, at the lowest spot, drill some holes in the bottom of the pipe so that the water can drain out. Well, how's the water going to get in there if I got it going into my basement and I got it going into a sealed box? Worst advice I ever had, because now every time I pull cables through that pipe, I get mud and water every time. So my advice is, read the manuals, what they say, listen to other people, and then make your own decision. J-bolts for a freestanding tower. You can see here the dimensions that are given for 120 foot. The best thing I found was when I came to Dayton, in the flea market, there was a whole stack of J-bolts. So I bought those, took them home, and started designing how I was going to lay this next tower out. I determined that I didn't want a tower that was too short, needed to be at least 120 feet, it needed to be a big base, but I didn't want to use a lot of concrete. So I started thinking about what I could do. You do know that when you pour concrete, it has to set for 28 to 30 days. So I built that into my factor. Also, the important thing is here, it talks about backfilling. Leave the forms on for at least 1 week before you take them off. Typically also, here's something that's very important. When you put the tower sections together, they're put together finger tight, erected, and then start at the top, tighten them as you come down the tower. It works so much better. This here is a Roan SSV 320-foot tower, starting with a 15 in at the bottom. In means it's knocked down, because these are knocked down and shipped all over the world. As you get toward the top, there'll be a 3W. W means it's welded. So you can have maybe a 3W, a 5W, or a 5 welded. A 5 knockdown is a lot of pieces to put together. So you can see the tower I'm using here is starting at a 10 and going up to a 5. I was thinking about going 140 feet, but then I said, you know what? I'm going to need a lot of concrete. How much concrete do you think it takes to put up a 120-foot tower, freestanding, self-supporting? Well, I didn't want to make a great big hole that was going to be 18 feet by 18 feet by 4 feet, which is 44 yards of concrete. At $100 a yard, that's $4,400 in concrete, plus I would have 44 yards of dirt to get rid of. Serious problem. But I figured, you know, this tower is really good stuff, so I'm going to start saving it. So I went on eBay, and for 10 years, I bought every piece of Roan 55G I could find. I'm sorry, not 55. This is Roan SSV. I have 55 also. The SSV tower was shipped in from Florida, Wisconsin, just all over the place. It came in different kinds of conditions, so I cleaned it all up, went out in the evening in the barn, worked for an hour. I limited myself to an hour. You know, that's all my wife could let me be out of the house every day for an hour. So I went out and scraped the tower, cleaned it all up, and I found out I had some duplicates. This is inside the barn in the work area. The piece of tower that you see together there is a 5N. That is very, very heavy. You can't even pick it up on one end by yourself. And I made little skids to move the tower around in the barn. In the foreground here, you see the cross members. When they came in, they looked very, very bad. However, you cleaned them up and then laid out the tower, and I put tags on every section to know where it goes and how it hooks together. The J-bars I were talking about from Dayton, you see them in that picture. I got all of those for $100. This was built on a very tight budget. It took 10 years to have the tower come in. I cleaned the tower up and sold off the duplicates. Many times you'd buy a 10-7-6 or something, or a 1-2-3, and I didn't need all those extra pieces. So I would make the money from the ones I sold to pay for the ones I was going to keep. On the left, you see the original cross members. On the right, you see the ones that have been refurbished. This is my work area, watching the paint dry. These here look more dry. This is coming along very nicely here now. And these are all laid out for construction day. Everything is marked and has tags on the other end. On the far end, you see the 5N is put together. And now this is the first section. This is number 10. And on the ground, you can see the template. You have to make a template to know where to pour your concrete and how to put the bolts in. So on the bottom of this 10 section, I welded together some steel. And then, of course, in planning the hole, you have to have the rebar cage. I went to a company that deals in metal, and I said to them, I need some rebars, and here's the dimensions. I took the dimensions from their own book. You can see that the sections are not spaced out equally. The rebar cage is 3 feet in diameter and 10 feet long, and they cost $200 a piece to get them made. There is no welding in this whatsoever. They're bent and put together very nicely. Now, I talked to you about the fact that we need the mark thing. Uh-oh, Tim. Something went crazy. I got 3 pictures. I hit something. I hit this here somewhere. Thank you for your help. Okay. Quality control is very important. Remember I talked about you had a template in the yard? The template then has a mark on it, and one corner of the tower needs to have a mark. Because when you go out to put the tower up, if you get the template turned from one leg to the next leg, it's not going to match up. And here is the yellow mark on the template. So I took the template out and put it in the yard where it was going to be and laid it out, making sure that we knew which side was up, so when the tower came out, it could set on the bolts properly. On the right-hand side is a rotating tower. It's 120 feet. The next one is a Roan SSV at 48 feet. And the next tower that you see there is a section in the yard that we're practicing with. And then by the barn is 120 feet of Roan SSV that we saw with the generator.
Now we're laying out the tower, and I asked my wife, I said, where do you think this should be? I had her come out there, and I said, where do you think this tower should be? And she says, well, put it right here. So I said, honey, let's drive a stake in the ground. So the stake is where my wife said the tower should be. So now it's time to start doing some excavating. You know, the previous towers, I used the backhoe and all kinds of equipment. You got all this dirt to get rid of, and they tear the yard to pieces. It's just terrible having the backhoe come in here. And I said, you know, I called the local excavating guy, and I said, you know, I want to make some holes in my yard, but I don't want to have any dirt left, and I don't want to tear up the place. And he says, well, we have this truck we'll bring in. It's called hydro excavation. I said, what's that? He says we use high-pressure water, and we make a hole by spraying the water in the ground, and then we use a big vacuum and we suck it up. I said, that sounds great, let's do that. I said, well, wait a minute, before you come, how much is this going to cost? And he says, well, it depends on your soil. I said, well, I got really good soil. He says, well, if you got really good soil, then we could probably do it for $200 a hole. I said, that sounds good, let's do it. So they made arrangements, and these sections that you see on this truck here are 5-foot sections. So right now, we could do a hole about 10 feet deep. Let's see what happens. Mark the ground where you're going to dig. He's got the suction ready to go, and we start spraying the hose, just like you're going to do a power wash. You're going to power wash your house. Instead, this time we're going to power wash the ground. We spray the ground like crazy. They start sucking it, and they get a little bit of dirt coming out, and pretty soon it looks like mud, and you got a hole forming. Well, I knew we needed to go down about 10 to 12 feet. We also wanted to flare out the bottom because it takes less concrete if you flare out the bottom. Remember, we're talking about 44 yards originally. This can be done for about 20 yards. Here we're digging the hole. We got to make the top a little bit bigger for the pad, and we're going to dig this hole straight down for 12 feet. However, at 6 feet, guess what we hit? It wasn't a coffin. It was shale. But the high pressure of this instrument they're using just cut right through that shale. Had it been flint, we probably would have had a problem. But since it was shale, they just cut right through it. And the vacuum here just sucked that shale right up into the truck. Well, you know what? Because they spent so much time cutting through that shale, they used more water than they anticipated. So guess what? My bill is going to go up because they had to bring in another truck. So they brought another truck in full of water because this whole principle works on the idea that we're going to use water pressure to dig this hole. So now we got to add another 5 feet. You can see they're getting ready to add it there. Going to put more 5 feet on so we can go a little deeper. And they were checking down to see how deep they are, but you know, you can't measure just by looking. So I got a meter stick. That's 39 inches, so we're a little bit more like about 48 inches. The string coming from the rope is 12 feet long. So now we drop the string down in the hole, and we can tell how deep the hole is and how large it is. Oh, it's time for a break. You can see the one hole over there is covered over. We don't want any deer falling in there. In Ohio, we have a lot of deer, maybe 17 of them in our backyard sometimes. We have one rebar cage there ready to go in the hole we're presently doing. And now we have the materials laid out and organized to continue our work. You see some other templates there. Those will be used to keep the to keep the J-bolt straight down in the hole later. We had to use a transit. When I walked out there, that ground looked perfectly level. I thought I had the best spot. But you know what? When we got the transit and shot the elevations, it wasn't level. I was off more than a foot in one direction. Here is a preliminary placement where the hole has been dug. It's 12 feet deep, flared out at the bottom. You never set the rebar on the dirt. Put bricks down there, put concrete block, put something so that the rebar is going to stay inside the concrete. Now we have the J-bars positioned. We have a template at the bottom to keep everything parallel and straight, and we're going to drop that into the hole. Here we're starting to put a little bit of the form for the concrete. The rebar cage has been dropped into the hole, but it hasn't been squared up yet. Overall view, we got 3 holes coming together. These skids come from the print shop. I'm in the printing business, so we have lots of skids, and I have lots of wood that we can make things that what we need. Forming up, this is the one I was off. I thought I was in a level spot, and I was off a foot on that side. But you can see the template there coming across, and now we got a hole that's practically ready for the concrete. The rebar cage is in the hole. You want to keep the rebar cage inside the concrete. You see the little rebar going into the side. That is only temporary. That would never be left there when you pour the concrete, because if the water in the soil will work its way back into your concrete if you have anything exposed outside the concrete itself. From the template on top, you see the yellow spot there, and then straight down is another plate the same exact size as the one above it. We also want to make sure that we put duct tape on all the threads, because the concrete is going to cover everything. This rebar cage has been stabilized. On the left-hand side, you can see there's a stake with the template coming across, and on the north side there's another one, and then the template down in the hole has been brought higher in to keep everything parallel. This one's ready for concrete. This one also has been stabilized, and it's ready for concrete. So the truck arrived, and the next truck came, and the next truck came. I usually do all my tower work myself, dig the holes, pour the concrete, finish the concrete. But doing 3 of them at the same time, I thought was going to be a little overwhelming for myself to do this concrete. If it was just, 20 yards in one hole, I could handle that. I told these guys before they came, be sure and bring a vibrator. I said, you got to have a concrete vibrator, because we got this rebar, and they showed up and they didn't bring one. And these are concrete finishing people. So I sent them home, and I said, you can't pour my concrete if you don't have a vibrator, and it needs to be a small one, because this is a small hole, and we got to get the concrete between the rebar cage. So they came back, and they brought the vibrator, started dumping the concrete in, and making sure everything was going to go well. The rebar cage will move. As soon as that concrete hits it, it's going to move. So you got to get a 2x4 there and pry it over to keep that rebar perfectly straight and where it should be. Here we're doing some more vibrating. Don't want to over-vibrate the concrete either, because then all the liquid comes to the top. So we're moving along nicely. We have 3 holes. It's all lined up. Everything is going good. Minimum soil disturbance. The ground is pretty nice, except for a spot there or two where they dropped some dirt. But we don't have any big heavy tracks coming into the yard. Everything's going along nicely. We're almost ready to pour another hole. This one here is just about finished, looking from the aerial view down, and now another truck comes. It took about a truck per hole. This one's almost finished. We got form is pretty good. Ground level is pretty nice. Now we're going to finish it smooth. The Roan book says when you finish this type of installation, you want to have a little bit of height under the bolts so that the water would drain off, and you use a smooth finish. The guys didn't want to do a smooth finish. They wanted to do a broom finish. Now, what's a broom finish going to do when the snow and ice gets on there? It's not going to roll off, is it? So we do a smooth finish. You get down, and you might be able to see, but there is duct tape around all those threads to mount that tower, because you don't want to get any concrete in there. This one is finished. Looks pretty nice. And here's a close-up showing the duct tape under the form. 28 days to go. So what are you going to do? Wait. The first week, I waited for the concrete to cure. And then the second week, after I took the forms off, I covered the concrete every night with concrete blankets. Shiny side up during the daytime, shiny side down at night. Went out every morning and evening and turned the blankets on my babies. After a few weeks, you're able to take the form off, and we're ready now to set the tower. This piece of tower has been sitting in my yard for 30 days because we had to put it together and make the form. So now we're going to take this over and set it on the J-bolts. Ready, set, go. Here we go. Driving over, set it on. Perfect. These guys were amazed. They said, we do commercial towers where it never even hits. I said, what do you mean it doesn't hit? He says, the bolts can be off 3 inches. He says, they don't even come close sometimes. And I said, what do you do when they're that far off? He says, we cut them off, and we get Hilti to come in and put new fasteners in to fasten that tower down because they didn't plan it well enough. You see the tag there on that piece of tower? That says that that's a 10N, and it says bottom. As I did get some guys to help me put these sections together, and I wanted to mark everything precisely so they have the right side up, and I don't want the tower to look like a broadcast tower with the small part at the bottom. Okay, we bring over some more sections. These sections are all put together by hand only and finger tight. You never tighten them with a wrench until they're vertical, and you never tighten it until the entire tower is up. The tower is up. I didn't show you all the pieces in between. The tower is up, and the 40-meter beam is on top. Well, it's not quite finished yet. And why is it not finished? Because we don't have any coax to the tower. Here's a close-up of the 40-meter beam. It's driven by a prop pitch. I have a thrust bearing on the top of the tower, a thrust bearing down below that, and then the prop pitch under it. So now you can remove the prop pitch, and the mast does not move. Very stationary. Below I added another 40-meter beam because you have a 40-meter beam on top. I didn't want to waste all that tower down below there, so I put another 40-meter beam aimed on the Caribbean. Because when you're running 40 meters at night into Europe and someone from the Caribbean calls in, you better answer him. He's going to keep calling all night. So you switch to the other beam and work him and then go back to running the 40 on top. Okay, now we need some feed lines, right? Well, my wife was getting ready to go to Florida, and I wanted to make sure that she didn't have a problem with me putting feed lines in and tearing the yard up. But you know, when I tear the yard up, I do it very neatly. I use a trencher. A trencher works very well, but you have to plan where you're going to put it. So I laid out the beams. Now, she's already left for Florida at this time, and I got a week to get this done. So I figured, okay, I'll lay the pipe all out and get a trencher and dig it. I went to a plumbing company to find out what the cost of the pipe was going to be, and they talked to me into letting them do it. They didn't have anything to do that week. So I said, okay, if you guys want to come out and you get this job done in a week, you can do it. And he said, okay. So I have 4 2-inch PVC pipes. I normally like to use continuous water pipe, big water pipe, but the price of this was so good I couldn't resist it, and they assured me that when they put it together, it would be sealed properly, and when they went together, there would not be a catch in the pipe, because when I pull the hard line through, I don't want to catch anywhere. So they assured me it would be a smooth surface inside all the way through. They also wanted to use a backhoe. I said, no. I can go downtown and I can rent a trencher, a walk-behind trencher, for $50 for the whole day. I said, you go get one. Well, they didn't get what I expected them to. They got this. It was okay. They made a trench, but the trench threw out more dirt than I would have done, and it was a lot deeper also than normal. But we put 2 pipes in the bottom and 2 pipes on top, so we have 4 runs coming into the house. So we trenched that about 320 feet from the tower back to the house, and now we have the sidewalk. Well, you know, the plumbers knew something. They knew how to get that pipe under the sidewalk without tearing anything up. And what they did, they took another piece of larger piece of pipe, they made a hole on one side of the sidewalk and a hole on the other side, and they got down in the hole and they shoved that pipe under the sidewalk, and then they cleaned the dirt out of the pipe, and then they put my plastic pipe through the first pipe, and they left it all in the ground. And so now nothing is going to fall apart and everything is good. However, they didn't understand the fact when I told them it had to be perfectly straight from the basement to the tower. No turns, no curves, no ups, and no downs. Perfectly straight. They didn't get it right, so they had to make some more holes. They felt that since it was 2 feet out in the yard, it was buried 2 feet, and when they got closer to the house, they could go uphill a little bit. Well, if you're going to pull hard line through there, 7/8 hard line, it's got to be straight. So we ended up not using the top 2 holes. We used only the bottom 4, and that's a perfectly straight run. It's got concrete on there and been sealed properly. And after we've got it all filled in, and I did put the landscape mulch back on, and my wife came home, she couldn't even tell I'd done anything. In the basement, we have 2 holes too many, but we can fill those in. So these are the 4 pipes coming into the basement, and then after the hard line was pulled, I felt that I was going to have to use a tractor to pull the hard line, so I got my Kubota out and hooked the pull line onto the 7/8 hard line and started pulling. Had some guys in the basement, and we pulled it through. Worked fine. Pulled another one through, just fine. Well, a couple of weeks later, I couldn't get anybody to come help. So I said, okay, I want to see if I can do this. So I went down to the basement, and I had the hard line all rolled up there. I put some lube on it, and I went out to the tower, and I started pulling the pull line, and it just came. I didn't know it. I didn't need the Kubota tractor to pull 360 feet roughly, 320, 360 of 7/8 hard line through a 2-inch pipe. If it's perfectly straight, you can pull it by hand, no problem whatsoever. Now, this is at the tower section. We need to put a box here because we want to keep the water out, and then when the coax comes down the tower, we'll have a junction box here because if there's any concerns later, you can go out and fix it. It's not going to be a continuous run from the house clear to the antenna. That's not necessary. We put the dirt back over. This was fun because I put the dirt back over, and then I go over with the tractor. Keep driving back and forth, push the dirt over, go over with the tractor back and forth until I got it to the point that I could put some grass seed on there and hope that I could water it real fast and it would grow before my wife got home. This is the box at the bottom of the tower. You can see there's also some ropes there because I also have a lot of pulleys on the tower that I pull other antennas up and down for dipoles. But looking from the bottom, there's the 40 meter aimed on the the 40 meter going to the Caribbean, and then the 40 meter on the top going towards Europe, and it's rotatable on the top one, but the bottom one is not. This is it, 120-foot Roan SSV completed in 10 years. It took me 10 years to save all the parts. It's been up now for 9 years. Thank you very much.
That's a wonderful feel-good story to end the antenna forum. Thanks very much for coming today. Hope you had a great time. We'll see you back here in this same room 364 days from now. 73. Don't forget the surveys. Don't forget the surveys.